Hi, welcome to the fourth question. The solution to this problem can be found in UTS Online. However, I would encourage all to try this problem manually on your own. The first thing I'll do here is I'll create a new tab. I'll do this by right-clicking the tab, choosing Insert, and I'll choose a new worksheet. Now, in this problem, we're using Newton's method, and Newton's method is basically an iterative technique that allows us to locate roots really quickly. So Newton's method is given by x sub n plus 1 equals x sub n minus f of x sub n divided by f dash x sub n, and f dash x sub the first derivative of f of x. The equation that we're trying to solve in the first problem is fx equals x to the power of 3 minus x plus 1 equals 0. Now, to use Newton's method, we will need an expression containing the first derivative of f of x. So this would be f dash x, and using simple differential calculus, this would be 3x to the power of 2 minus 1. Okay. We can now plug these numbers, these equations, these two expressions into our Newton's method formula above. And this would be x sub n plus 1 equals x sub n minus x sub n to the power of 3 minus x sub n plus 1 divided by 3x sub n to the power of 2 minus 1. Now, implementing this formula is fairly straightforward. I'll create a spot that contains our initial guess, and that's called as x0. Our initial guess will be 1 in this case. In order to obtain a good initial guess, I would always highly recommend that you create a simple plot. And this plot allows you to visualize where the root may possibly lie. The root will be where your curve intersects the horizontal axis. I'll also create a spot where I'll keep my tolerance, and tolerance is just a predefined limit that determines we should be iterating or stop iterating. And the tolerance is going to be a very small value. In this case, I'll just use 0.00001. The next thing I'll do is I'll create a table containing these values. So we'll have iteration x of n, f of x sub n, f dash x sub n, x of x sub n plus 1, error, which is also known as delta x, and we'll have our test. The iteration will start from n equals 0, and iteration is actually n. So this would be 0, 1, 2, 3, 4, 5, 6. I'll leave more guesses than necessary. So x sub n will be minus 1. Minus 1 is actually where my initial guess should be. You can obtain this value, like I've said, by drawing a plot so that you can visualize where the roots may possibly be. F x sub n will be this number to the power of 3 minus cell G5 plus 1, and f dash x sub n will be 3 times x sub n to the power of 2 minus 1. X sub n plus 1 will be x sub minus this value, so divided by this value, and error will be the difference between these two values here. We are only interested in the absolute error, so I'll use the ABS function. This will be cell G5 minus cell J5, and we'll create a test to determine if we should keep iterating or if we think the results are small enough, are close enough. So this would be if the error is larger than our predefined reference, and I'll keep cell G2 as a fixed reference. If this condition is true, we will keep iterating, else we can assume that the result is close enough. This cell G6, which is x sub n, has been found in the previous iteration. So this will be equals cell J5, and I should be able to copy this group of cells into the next row, and I'll do the same thing with the entire row number 6. The results seem to be mostly correct, but there's one minor error. In my if statement, I'll need to make a small adjustment to this formula, and I'll need to keep G2 as a fixed reference by holding the F4 key, and that should work. All right, so that is my results are in iteration n equals 4, and the value of that satisfies our original equation will be minus 1.32472. Okay, so that's it for the first problem. I'll repeat the same thing with the second problem. The second problem is very similar to the first, but we have a different equation. Our equation this time is f of x equals e to the power of minus x plus sine x. The first derivative of this expression is f dash x equals minus e to the power of minus x plus cos x. Okay, so that should work. I'll copy and paste the contents of these cells into the next problem, which would save me a little time, and I'll use an initial guess of 2. Again, you can obtain you can gain an approximation of where the root may possibly lie by drawing a curve, and you can see where the curve is intersecting the horizontal axis. That point of intersection would tell you, would give you a good approximation for initial guess. So this will be iteration 0, 1, 2, 3, 4, 5, 6, 7. X sub n will be 2. F of x sub n is exp, and exp is a function, is an inbuilt Excel function that returns e raised to the power of a given number. So this would be exp to the power of x sub n, minus x sub sine G17. This formula will be minus exp minus cell G17 plus cos cell G17. And x sub n plus 1 will be x sub n minus cell H17 divided by cell I17. The error will be the absolute difference between x sub n plus 1 and x sub n. So this would be ABS, cell J17 minus cell G17. Our test will contain an if statement comparing our calculated error against a predefined tolerance. So if our error is larger than our predefined tolerance, We can assume that we need to keep iterating, else we'll assume that the results are close enough. Now we're nearly finished. X sub 1 will be 3.894228, which we calculated in the previous row. And I'll just copy these cells to the next row. I'll then copy this entire row to the next couple of rows, and we're nearly finished. That is, our results look our results in fact look incredibly good. The results that are of interest to us would be in this row, and we don't have to keep iterating after the error is found to be smaller than our predefined tolerance. So our result is x equals 3.183063, and this number will be a solution to our original equation. I hope you enjoyed this video, and I look forward to seeing you in the next one.